Hello friends, welcome to Sri JCBM College YouTube channel. In this video, we are going to talk about first and second shifting theorem of Laplace transform or translation property. In previous video, we have seen introductory and definition of Laplace transform. With the help of that definition of Laplace transform, we are going to prove first and second theorem of shifting or translation property. In this lecture, we are going to see proof of first and second shifting theorem of Laplace transform. And now let us start with the statement of first shifting theorem. First theorem or translation property. Statement: if Laplace transform of function f of t is equal to f of s, then Laplace transform of e to the power at f of t is equal to f of s minus a, where a is a constant and f of t is a given function which is in time domain. So, very simple proof. We have to prove this condition, Laplace transform of exponential at f of t, and we are going to prove in the frequency domain f of s minus a. So, proof of first shifting theorem. So, we can prove this theorem or this condition with the help of the definition. So, already we know that the definition of Laplace transform, by definition of LT, and that is Laplace transform of f of t is equal to integration, limits are 0 to infinity, e to the power minus st f of t dt. Also we can equate in the frequency domain, that is f of s, and we call equation number. With the help of this definition, we solve this condition. So, our f of t is nothing but e to the power at f of t. So, just replace this term with the f of t. Just replace f of t instead of e to the power at f of t. So, just substitute in definition, which implies Laplace transform of f of t. F of t is given. Look at this condition. Our f of t is nothing but e to the power at f of t. So, substitute in place f of t, Laplace transform of e to the power at f of t is equal to integration 0 to infinity e to the power minus st, and f of t is nothing but e to the power at f of t dt. For simple simplification, so when bases are same and powers are add, integration 0 to infinity. So, here bases are same. So, e to the power minus st plus at into f of t and dt, and take common t, e to the power, take the minus also common, s minus a and t f of t dt. Dear student, now observe this condition, and which is looking like as our definition of Laplace transform. So here in the place of s is there s minus a, just we can write f of s in the form of s minus a. So here s minus is there, instead of s is s minus a is there. So definition of Laplace transform, so that is f of s minus a. So therefore Laplace transform of e to the power at f of t is f of s minus a. This is the proof of the first shifting theorem, very simple proof. And here just we have to replace s as a s minus a. And one thing here we have to see, suppose e to the power at is there, then s minus a. Suppose this is a minus, and definitely it converts in positive. So please remember this one, and here I have taken positive, and so in answer will be in minus. This is the first shifting theorem. We try to understand this condition with the help of examples. Suppose a Laplace transform of e to the power t into sin t. So we are going to solve this one. So this is the first shifting theorem. We have to apply here first shifting theorem. First we have to find out the Laplace transform of sin of t, and that is 1 by a square plus 1 square. The general form of Laplace transform of sin of at is a divided by a square plus a square, and these are the elementary, some standard elementary function of Laplace transform. In next video we go through the details about it. Just I am telling how to works this condition with examples. So now, so Laplace transform of e to the power t sin t is equal to 1 divided by, just we have to change coefficient of t as a, in the place of s minus 1 whole square plus 1 square. Just we have to replace s as a s minus 1, because coefficient of t is nothing but 1. And now look at the definition of the first shifting theorem. Here a is 1, so we can write s as a s minus a. So here s changes s minus 1, and this is the solution of Laplace transform of e to the power t and sin t. So this is the one of the example for first shifting theorem, and we can see the so many example for first shifting theorem in next video. Now we will see second shifting theorem of Laplace transform. Let us start with the statement of second shifting theorem. Statement: if Laplace transform of function f of t is equal to f of s and g of t is equal to f of t minus a if t value is greater than a, and g of t is equal to 0 when the value of t is less than a. And then we prove that Laplace transform of g of t is equal to e to the power minus as into f of s. So this theorem also we solve or we prove with the help of the definition of Laplace transform. Proof of this condition with the help of definition of Laplace transform. LT. So we know that Laplace transform of f of t is equal to integration 0 to infinity e to the power minus st f of t into dt, also we call f of s, we call equation number 1. So we are going to solve g of t, and now we have to apply the Laplace to the function g of t, which implies Laplace transform of g of t integration 0 to infinity e to the power minus st. Instead of f of t, just substitute g of t dt. Dear student, look at this condition. G of t is splitwise function having a two limit value. When g of t is equal to 0 and t value is less than a, when g of t is equal to f of t minus a if t value is t greater than 0. So now with the help of integration property, we have to split up the limit values. So t value is less than a, it means 0 to a e to the power st g of t dt, plus when t values are greater than a, then limits are a to infinity e to the power minus st g of t into dt. So this g of t, when the limit value t value lies between 0 to a, then condition is given g of t is 0, and this is nothing but 0 when limits values are 0 to a, and remaining terms limit value a to limit infinity e to the power minus st g of t and dt. So therefore, so Laplace transform of g of t is equal to, and our g of t is nothing but when the limits values are a to infinity, and this is our f of t minus a. So g of t is nothing but f of t minus a. So here limit value is a to infinity e to the power minus st, and g of t is nothing but f of t minus a to dt. With the help of substitution method, we have to consider t minus a is equal to u. So here we require dt and t also, and this implies t is equal to u plus a, and differentiate with respect to t. So dt is equal to du, and simultaneously we have to change limit value also. When t is equal to a, and what is the value of u? So substitute t value here, t is equal to a, then this is the 0, that is u also 0. And also when t value is infinity, and what is the u value? So t is infinity, then u also infinity. Just substitute these values in condition 2. From 2 Laplace transform of g of t is equal to, limit values are 0 to infinity, and e to the power s, and t is as taken u plus a, and this one is f of t t minus u consider as a u. So, t minus a is equal to u and dt is nothing but du. For simplification, e to the power minus su into e to the power minus sa f of u and du. Now take e to the power sa and integration 0 to infinity e to the power su f of u and du. And this function or these terms converted in the form of u. So, when you change the variable, there is no effect on any term of this condition. So, it minus e to the power sa integration 0 to infinity e to the power, I will take u as a t again, f of t and dt. So, now look at this condition which is looking like our definition of Laplace transform. So, we can write minus sa of frequency of the s. Therefore, Laplace transform of g of t is equal to e to the power sa s minus a, and this is the proof of the second shifting theorem. So, we will discuss examples on first and second shifting theorem in next video.